Hello, everyone. Yeah, that was okay. That was a bit loud. I'll be quiet. So, today we're going to be talking about compilation time. Who who has a problem with compile times in Scala? Nice. All right. So, it's me and Iulian Dragos. We are the co-founder of Triplequote. We've been fairly active in the past 10 years in the Scala community, working on different mainstream projects. And, well, among other things, we've also been part of Lightband, TypeSafe, and even before that, Scala Solutions. But we decided to create Triplequote because our mission is to cut down on compile time, on sword fights due to long compile time in the Scala community. So, have you ever felt this way? We all feel the Scala is such a great language. We all feel so much productive with it, but are we? Have you ever thought about all the time that you're wasting just waiting for the compiler to get back to you so that you can move on to the next thing that you want to do? Well, I definitely felt that way, and I got to wonder, what can we do about it? So we're not the first one thinking about it, and in fact, you can go and build sophisticated technology to pull you back to work once the Scala compiler is done with its work. But yeah, that's not too bad, but can we do better than that? Can we actually fix and improve Scala compile times? Of course, we think we can, and this is what we're going to be talking about today. So I start by discussing the state of the Scala releases. Can we say anything about compile time as new releases of Scala are happening? And then we'll spend a bit of time seeing what are the tooling available today that can help us investigate and detecting those compile time inefficiencies. And last but not least, we'll talk about Hydra, which is our product, and hopefully you'll agree with us that it's the free lunch. You can just use Hydra and reap the benefits of compiling faster your Scala code. All right, so Scala releases. Scala 2.12 was released back in November, and many great features, but the one that I really like about it is the fact that they target, well, Scala 2.12 targets the Java 8 runtime. So it actually takes advantage of all the goodnesses that are available on Java 8. So what does it mean for us? Well, we got reduced binary footprint when we compile Scala code. Why? Well, because the Scala compiler now has a different encoding for traits and a different encoding for lambdas, and it's using what is available in the in the Java 8 runtime. This is awesome, and I'm extremely thankful to the Lightband Scala team for doing that. It's a great thing. But what about performance of the Scala compiler? What can we say about if we compare 2.12 performance with 2.11 performance? Well, if you talk, at least a couple of months ago, we talked to Miles Sabin, the author of Shapeless, and for him, actually, combining shapeless test with 2.12 was lower than with 2.11. So that was, of course, is not ideal. But on the other side, if you talk to the Scala team on their benchmarks, they seem to have better compilation times with Scala 2.12, which is great. So what can we draw from that is that it's not easy to tell whether Scala is getting any faster as we get new releases. But the good news about it is that the Scala team, well, acknowledged that problem and is working on it, is actively working on it. And they're working on automatic benchmarking so that they can detect if there was any regression happening maybe in one of the past releases, so that they can correct the problem now. And they also can make sure that there's not going to be any other regression that goes unnoticed. Any change that, let's say, brings down compilation time, it will be visible, and it will be up to them to decide whether the trade-off is right. So it kind of leaves a question for us. They're working on improving compilation speed of the Scala compiler. So we're done. We don't have to do anything because they're gonna take this problem for them and they're gonna solve it for everyone. Of course, it's not the case. We can do still plenty of, I'd say, silly things in our code that have a huge impact on compile times. Just think about how you define and use implicits, or maybe you define some macros. All these things, of course, they're gonna add up on your compile times. And so you want to understand what's happening, and potentially you want to detect and fix inefficiencies that you're adding in your code base. So what can we do? I'd say the first thing is that we need to be aware of what are the existing tooling that can help with the task of, well, on one side, detecting inefficiencies, and on the other side, fixing them. And this is what we're going to be looking at in the first part of our talk. So the Scala compiler has a bazillion of options. I don't know if you've ever explored them, but if you do Scala C minus X or Scala C minus Y, you'll see many, many, many options. And some of them are extremely useful to help you bring down compile times. So there are some really easy ones that you can use tomorrow or today and immediately spot if you have dead code. So code that is basically there, but it's not used by your application. And of course, the less code you need to compile, the faster it will be. So of course, every and each of these flags has an overhead. As small as it is, it's still an overhead. So maybe you don't want to run them every time you compile locally, but I'd say you should definitely put them on your CI so that at least you get the information. Maybe there is some code that you can remove, and having the information on the CI, I think it's a cost that it's okay. But I'd say that those are the low-hanging fruits, are the easy ones to catch related to compilation speed. And the other thing I would say is that you're probably not going to get 10, 20, 30% speed up by enabling those flags and removing that code unless you have a lot of that code in your application. So what do you do next? Well, the next thing is that you'll have to be wearing your detective hat and sort of be ready to understand what the compiler does, understanding, actually how Scala treats your code and compiles it into bytecode. And there are a number of flags that can help you with spotting inefficiencies when it comes to compile time. The first one, I would say, minus verbose. So minus verbose gives you a ton of information that I'd say you don't care about when you're looking at compile times. But there is one thing that is extremely useful. It gives you the compile time by phase in your program. So as you may know, the Scala compiler has many phases. So your program goes through many transformations. There are actually 25 in the Scala compiler. And what minus verbose tells you is how much time is it taking every phase for the compilation. So that gives you some initial hint about potential problems that you may have. Another one that is really useful is this minus x print, and then you have the phase name. So what minus x print gives you is the abstract syntax tree, so the AST, that is seen by the compiler after the given phase. So if you don't know what are the phase or the phase names in the compiler, you can just use minus x show phases, and that will list all the phases in the compiler. And then let's say you want to compile, you compile one source file, you pass the option minus x print, that let's say typer, which is type checking, and you'll see what the code looks like after the type checking phase. And I'll tell you a bit more about why this is useful in the next slides. Then if you think implicits may be the reason why it's taking too much time to compile, then minus x log implicits, it gives you a trace of which one are the implicits that the compiler attempted on your source files, but they did not succeed. Of course, the more implicits the compiler is attempting, the longer it will take to compile. And last but not least, if you are using or depending on code that uses macros, it might be useful to know about these other two macro flags that gives you insights into what the compiler is doing during macro expansion. So in my experience, or in our experience, I would say, those are the flags that have been extremely useful for pinpointing compile time inefficiencies. So how do you start? Well, let's say start by using minus verbose on your code base. Get a view of your compile time by phase. So this is basically what it would look like. Of course, you don't get a chart as an output. You get numbers, but then you can put it on a chart. So on the y-axis, we have the compiler phases. And on the x-axis, we have the time that it takes for each of these phases. And here we're basically comparing two projects. One is the Akka actor module, and the other is a project that we've been working with. So we've been doing some consulting work with Zalando and to help them cutting down compile times. And this is basically what we have seen when we came to, when we arrived to the project. We were seeing that Well, there is one thing that is jumping to the eye, right? There is that huge green bar. And what do you think is that phase? Does anyone have a guess for that? Parser. Parser. It's not that. It's typer. It's type checking. What a surprise. So type checking in that project was taking an awful long time. It was taking 32 seconds out of the 55 of the old compilation time. So more than 50%. And the reason for that is that that project was using some type-intensive library. And of course, it takes time. Well, the type checker has to do more work. He has to generate things. So it's definitely a costly operation. But maybe it was taking too much time. In fact, it was definitely taking too much time. And I'll tell you a bit more about this in the next slides as well. And so whenever you see the typer is taking more than 50% of the type checking time, I would probably say even more than 40%, it might be OK, but you should know why. If you don't, then I think it's your opportunity to investigate and understanding what's going on. And usually, if typer is around 30%, as it is the case for the AK actor module, I'd say that's normal. 30% is about what you can expect. So you investigate, and what do you focus on? Well, there are usual suspects for long compile times or long type checking time. Usually it's type checking, as I said. And what is that takes time? Well, there is macros and macro expansions. There is implicits. And there is also, I would say, well, sometimes there is a correlation between macros and implicits, because sometimes you can have implicits that are implemented with macros. So this is definitely a case when it can be really costly to execute that, to compile that code. And last but not least, there is also type inference. As Martin said in his keynote, there are cases where it can be costly to infer the type. Of course, there's been many improvements to avoid those problems, but there are still possibilities when it takes time to generate the type, and so you can get some easy gain. And in fact, I think it was about a month ago or 2 months ago on Twitter, I saw this tweet from someone contributing to IntelliJ, where they said that by putting explicit types, they got 17% speed up just by that. So I'm not saying that that's what's going to happen in your code base, but maybe it's something that you should try. Maybe just by adding explicit types, you're going to get some real boost at compiling. All right, so how do you go about identifying problems? Well, the first thing is that you want to focus your effort on some source file. So you basically want to know what are the source files that are being the more costly to compile. The bad news about that is that there is no tool at the moment that can help you with it. We're actually working on this exact problem, and Julian will tell you a bit more in the second part. But if you have a guess for what is the source that may be taking a lot of time to compile, maybe because you're using some type-intensive library in some place, well, then you can validate that guess by compiling that single source and see how much time it takes in isolation. If you see that it takes more than expected, well, then that's where you should put your effort and investigate. So how do you go with that? Well, you want to print the tree of that source file after typer, and you want to look at it and see, is there a huge amount of code that is generated that was not in the original source? If that's the case, then macros are at play, and that's likely the reason why it's taking so much. Or is there any complex or long infer type? That's another reason why, that could explain why it's taking so long to compile. And in case none of those are actually an explanation, or you're not using macros, then I'd say that most likely it's because of implicits. And if it's because of implicits, use -x log implicits to get a trace on that source file of how many implicits have been attempted by the compiler, and that will tell you why it's taking so long to compile. So we're talking about implicit resolution. Who knows how implicit resolution is done by the Scala compiler? OK. I'd say, I don't know, maybe 20%. So yes, I'd say this is a tricky subject, but it's extremely interesting on one side. And I definitely think that every Scala programmer should understand or at least it should have an intuition of how the Scala compiler does it, because it plays a huge role on your compile times. So you want to learn about how the Scala compiler does implicit resolution? Well, you should go and read chapter 7 in the Scala reference. The Scala reference is actually very readable. It's not just made for a PhD student. It can be read by any one of us. And it gives you a formal definition of what the compiler does. So you get a really good understanding of what's happening.
Shall we take a 10 minutes break?
Yeah, we can do that. Good, but yeah, maybe not. Let's build an intuition of what the compiler does. So we have this code that I would definitely not recommend that you write, but let's say that we have that show method that takes a map, and then we're calling that method passing just an employee, which is definitely not a map. So for that to compile, we know that the compiler is going to look for an implicit, right? If it can't find it, it will fail. We will get a type checking error. But let's say that it will succeed. So what is the compiler doing to make that, to make that statement work? It will start by looking at the current scope. It will basically see if there is any implicit definition, yes, defined in the current scope, so it's available without prefixes. And if there is an implicit available such that employee can be transformed in a map of ID employee, it will apply that implicit, and basically will yield our expression so that the code type checks, right? Well, let's say that it doesn't find it in the current scope. Do you know what's going to be the next step? Is it going to bail out, or is it trying to do some more work? It's not going to bail out. There is something else called the implicit scope, and we're going to see what it is. So this is what I told you. At the beginning, it's going to look at the current scope, so everything that is available without a prefix. If it can't find an implicit that works for that expression, then it will look at the implicit scope. So what is the implicit scope? Well, in this case, we had a show method that takes a map, right? A map of ID and employees. So the implicit scope is basically defined by all companion objects of the target or the caller type. So in this case, we have employee, which is the starting type, and we have a map as the target type, because this show method takes a map. And what the compiler will do is looking at the companion object of those types to see if there is an implicit conversion that the compiler can use to transform an employee into a map of ID employees. If it can find it, it will apply it. Otherwise, it will just reject the statement, and it will issue a type checking error. So in what companion object is it going to look? Well, it's going to start with map, looking at the companion object of map, not finding anything, because, of course, employee is our own class, so I'm not going to be finding something in a library that is provided by the Scala library. So it's going to look into ID, in the companion object of ID, and in the companion object of employee. But that's not it. The compiler will also look into map is a compound type, so it extends other types. So it will also look into the companion object of seek and iterable, and so on. You can see that it's a recursive algorithm. And that should also kind of gives you a hint that, yeah, it takes time. Just because there are many potential types and companion objects, and potentially there are many implicits that it will have to look at to see if there is one that matches. Good. So the takeaway is that, yes, implicit resolution can be costly. And the one tip that we can give you is that try to limit the implicits that you have in the scope, so the ones that are available without any import. And push, so what is it? Like, you make an import, you import an implicit in the current scope, then that's an implicit that is available in your source file. Or maybe you define an implicit in a package object, well, then that implicit is available to all classes in that package, right? So that's something you should avoid. So where should you put your implicits? You should try to push them into the implicit scope. The reason is that you want the Scala compiler to look through the implicit in the current scope really quickly, and then just look into the companion object, which is where your implicit should be. That's where you want the compiler to look for those implicits. And as I guess something to support this point is that when we were at Zalando working on that project I mentioned before, it turned out that they had some implicits declared in the companion object, and not in the companion object, sorry, in the package object. So those were implicits available to every class in those package, and they were very expensive to compute. And actually, the compiler was attempting to, well, it was computing those implicits many, many, many times. And by simply moving those implicits from the package object to the companion object, we brought down compile time by 40%. With that single change, it was like literally changing 3 lines of code. And that was a huge boost. If you want to learn more about the kind of work that we've done at Zalando, I put a link. Feel free to explore, and then if you have questions, just tweet us, and we'll be happy to tell you more. So, what was happening at Zalando was an interplay between implicits and macros. So macros are great, right? We love macros because they let us reduce the boilerplate. We don't have to type things. The macro will do it for us. Problem is that the macro will do it for us every time we compile, right? So if it takes time, that means that we're going to wait every time we're compiling. And, well, macros can be responsible for 80, 90% of compiling time. Of course, that depends on what the macros does. A macro can do anything. It can trigger type checking. It can trigger type checking multiple times. So just imagine, you may potentially be spending a lot of time just during macro expansion and type checking that macro. So the takeaway for me would be not that you shouldn't use macros, but you should be pragmatic about how you use them. Be aware of the cost, and sometimes you're maybe better off just maintaining some boilerplate instead of using macros. Right, so it's simple, right? Now you know everything about how to pinpoint inefficiencies. It's a really simple job. You have these few flags, easy peasy, right? Of course it's not. You saw it. It takes time. Probably takes 1 or 2 days. You need to be aware of what the compiler does. And so now I'm going to pass it to Julian, and it will tell you how you're not going to have to do all these things because Hydra can do it for you.
Thank you, Mirco. All right, so now for something completely different. Probably by now you've heard about Hydra. So this is our project and our vision to speed up Scala compilation. And Hydra is really, I would say, a fairly natural idea. That's how we started anyway, to try to distribute building Scala files, or at least as a first step to parallelize compilation of Scala sources. So obviously, if we take today's presentation as an example, we're going to probably run out of time. And that's because I had to wait for Mirco to finish talking before I could start talking as well, even though the 2 parts of the presentation are fairly different and distinct. So wouldn't it be much better? We could cut the whole presentation time in half if both of us started talking right after the title slide. So taking this natural idea, we thought, well, there's 2 other things that I would like from my tooling. One is to be transparent, in the sense, I don't want to worry about parallelizing. I want to just be able to turn on a button or flip a little knob and have it working. And the same way I can go back to my regular single-threaded or vanilla Scala compiler if for whatever reason I have problems. And the third one is what Mirco was just talking about, is insights. I would like to know when compilation is slow, why it is slow. And maybe what parts of my project are slow, because often they're not. Not all files take the same amount of time to compile. So while this sounds easy, we first sat down and thought a bit about how should this work. So we can distribute files to worker in the cloud, let's say, or several machines, and just gather the results. And this has 2 hard problems that we would need to solve. The first one is inter-file dependencies. You may send files to different workers, but they might still need each other. Maybe they call into one another, or they extend each other. There's a class and a subclass, and so on. And the second one, a distributed system is a complex beast. So once you go distributed, you have to worry about a number of issues. So before we set or embark on such a difficult journey, let's see if it's worth it. So we did a little bit of math. So Amdahl's law is a way to predict the speed up you can get from parallelizing parts of an algorithm or of a program. So obviously, it's fairly impossible to parallelize everything unless you have an embarrassingly parallel problem. So we have two constants in there. P is the chunk or percentage of the work that could be parallelized. And S is the speed up we can get for the parallelizable work. So that is roughly the number of cores we can throw at the problem. So the speed up would then be bounded by the constant work that we cannot parallelize, 1 minus P. So in the ideal case, the maximum theoretical speed up really depends on how much we need to sort of do in every worker. So these are some values we put there. If 50% of the work cannot be parallelized, then the maximum speed up I can get is 2 times. Basically, the rest after the 50% mark takes 0 seconds, and then I made my compilation twice as fast. And so on. So for 10%, obviously, that means 10x speed up. Now, the problem we had with this is that we kept looking and looking, but couldn't find any hardware with an infinite number of cores. We're usually stuck with 4 or 8 on a laptop. So more, let's say, realistic numbers would be something like this. What we can typically expect. So we can, let's say, expect a 2.5 speed up if we use 4 cores and the constant work, the part that cannot be parallelized, is 20%. So from our measurement so far, that's also the area where we stand. Because you can use the law in the other direction too. If I measure the compilation time and I know how many cores I used, I can extract the constant. And this constant number is actually quite nice because it works it's a specific number to a project. It's project specific usually. Actually, it's different between main sources and tests, much lower for tests. And we can use it also to predict performance to a certain extent. So maybe one other interesting thing to notice is that even if I doubled the number of cores, I will not really double my speed up. So in case of, let's say, the happy case of only 10% constant work, I can go from 3 times faster to 4.7 times faster by doubling the number of cores. Let's see now. We said, well, this is worth it, obviously, since we're here to present it. Let's see how do we do this. So we started with 1 machine. So Hydra Today is just parallel. It's not distributed yet. But we can still use all the cores we have on 1 machine. And the granularity at which we work, so the level of parallelism, is a single file, source files. And the way we parallelize it is to simply have several Scala workers that take the source file from source and go all the way to bytecode. That means that the whole pipeline runs in parallel in each worker, including typer. And the hard problems, well, we have 2, let's say, if we go a little bit deeper than in the first assessment. Interfile dependencies between workers. We still have that problem because we have independent workers. And there, our solution was to basically duplicate some work, but make sure that we share as much as we can between workers in order to keep getting the speed up. So that's a little bit vague, but I can't get into too many details on the stage. And the second problem is that the Scala compiler is very performance aware. So there's been a lot of work going in Scala C to make it as fast as it can possibly be. That means that there is laziness and there's mutable state for good reasons, I would say. So that also makes it harder to parallelize. So we can't really use shared state safely, and we don't do that. At least we started with a share nothing architecture and then have very controlled sharing between workers in order to still get good speedups. Actually, just as a parenthesis on the laziness and mutable state, I hear very good news about Scala 2.12.3, and there's going to be pretty nice speedups in the single-threaded case as well. Which obviously is good news for Hydra as well, because if we can get down that constant factor, we can also parallelize better, so we can get better results. So how well does it work? These are a couple of open source projects that we measured. So Specs2, core and test, I think. We get between 2.2 and 2.5 speed up. So that's, if we go back to the table with Amdahl's law, we're probably somewhere between 10 and 20% constant work, maybe even less. Shapeless, we have the JavaScript core and the JVM core, so the speedups there are a little bit less good than for Specs2. Okay, yeah, it's not on this chart, but our best speedup, and I didn't put it there because it's maybe a little bit atypical, is for Scala debugger tests that were 6 times faster. So in that case, the constant speedup, the constant factor was 6%. So tests usually behave a little bit better because they have less interdependencies, obviously. Okay, so we talked about shapeless, but shapeless itself is a fairly small code base. If you look at the actual number on the bar chart, you see that compilation time takes, what, 15 to less than 20 seconds, or for the JVM one, less than 15 seconds. So shapeless itself is fast to compile, but what everyone is suffering from is actually using shapeless, which means shapeless tests would be a more interesting project to look at. So these are the numbers. This is all based on 2.12.1. I would say 2.12.2 is probably the same. So on this case, we get a 3 times speed up. What I was saying, tests usually have a much better constant factor in there. Obviously, what I didn't really say is that the more cores you throw at the problem, it doesn't necessarily mean that you will continue improving the speed up every time, because Scala is it's a memory intensive process. So depending on your hardware, you get memory bound quickly, so the memory bus will just get saturated. So if you have more workers trying to read and write to memory, you will just make everyone slower. But if you have Intel Xeon-based hardware with very good memory bus, you can go way further than 4 cores. All of these measurements are using 4 cores, by the way, on a MacBook Pro, so i7. Also, all the times we've shown are warm compile times, but it's nice to see how it would behave on the CI, where it's all cold JVM. So warm JVM means that you've run your loads several times so that the Java virtual machine has finished just in time compiling your code, loading all the class files from disk, verifying the code, and so on. So these are the curves we get for one of the projects. You can see that the speed up is quite consistent. I think it gets slightly better on a warm JVM, but it's still pretty good already from the first run. Yeah, as a parenthesis, measuring JVM performance is quite a tricky business. So I just want to quickly mention that the Scala team has a pretty awesome setup now for benchmarking Scala, and I hope one of them will at some point give a talk about how to properly measure Scala C performance. Because there'll be a
blog post on it in the next week or so.
Awesome, thanks. So yeah, go ahead and read Seth's blog post when it comes. Or Jason's, well, Scala team's blog post when it comes out. And it would help us as well to link to it and show it to everyone. All right, so how is the Hydra compiler working? Well, there's several components in there. One of them is a Scala C fork. We hope that this won't stay forever a fork. We're pushing patches upstream when they make sense, and I hope we will manage to unfork it soon. We support 2.11 and 2.12, so starting with 2.11.8, so there's a certain amount of work that's sort of in the past, but hopefully for 2.12 and onwards we can get rid of the fork. One thing that's maybe good to mention, this is a drop-in replacement. It's not an SBT plugin. Even though there is an SBT plugin, this can work fairly well on the command line if you just want to quickly test it. Other forks, in particular the type-level Scala fork, should work as well. We don't support it currently, but I don't see any reason why, if there is demand, this would be difficult to do. And one question we get often is, how do we make sure you're not breaking our build? So what we guarantee is binary identical output. You can compare the class files that you obtain with Scala C and Hydra, and they should be the same. There are sometimes very slight differences in the order of methods, but absolutely everything else is identical. And I think we can probably get rid of all of those as well. So the last part of the three pillars, insights, this we started by saying, well, if we're going to distribute the build, we want to know how the workers are doing, and sometimes workers can get unbalanced. And the reason why they get unbalanced is that all source files are not equal. Some of them can take a very long time to compile. So you would like to know that you have a worker that takes 200 seconds to compile, while everything else finished in 30 seconds. And we had such an issue with one of our clients who was saying that I can't get any speed up out of Hydra, and we have around 190 seconds with Hydra and 200 something or 250 with single-threaded compiler. And then when we sat down and looked, there was one file that was taking 200 seconds to compile, or 190, whatever. And that was just one file that stayed in one worker, and everybody else finished in a 10, 15, 20 seconds. So we said, OK, we have to do something about it. We have to help the users know about this. And then naturally, we moved on to more detailed metrics than just the time. So in that particular case, we could track it down. Maybe it took us a day to find the exact combination of imports and macros, expansions, and so on that were taking literally, I don't know, 500 lines of code file into 40,000 lines of code. So that's I would say, quite impressive as a feat. So we could take it down. So what we want to do is to get this kind of monitoring or metrics and build some sort of dashboard or UI where you can see your builds historically as well. So you can see, well, last week my build was much faster. What happened? What is the commit that slowed it down? What is the file that got slower? Or is there too much GC load? Maybe I just need to give it 8 gigabytes of RAM of heap instead of just 6. And that's why it's slow. So how would you, well, yeah, the transparent, actually, this is the last pillar, transparency, which is also the simpler one. The way to use it, if you're using SBT, is to simply add a compiler plugin that sort of plugs into the compile task, and that's all you need to do. Other build tools will come. So far, we didn't do it, but I guess if there is a lot of demand, we can look into that as well. On the command line is just another minus CPUs flag that you can say, oh, I want to use 4 workers, and that's about it. So obviously, I didn't mention it, but Hydra is our business. So we're trying to build a business on top of Scala tooling. How do we, though, contribute back to the community? And this is a thorny issue, of course, because we build on top of what the community build, and we want to give back. So we're pushing patches upstream. We depend on Scala working well, and we depend on SBT and Zinc working well. Of course, once I'll talk about the timeline a bit later. Once we reach the general availability, we will provide open source projects with licenses as well. So it will be free to use. And the last point, which I want to mention as well, is that we will implement a SIP25, which is about adding static fields and methods to Scala objects. Hopefully, this will make it into Scala 2.12.3, so it's really soon now. We started working on it. The PR is not out yet, but hopefully it will be out soon. So the timeline, at this point, and I think until the end of Q3 this year, we started a private rollout. That means we're working with clients who have a relatively large build, so it takes many minutes to build, and we're working closely with them to find all the issues, if there are issues, and help them get the best speed up possible. And at the same time, we're working on the insights and metrics that I mentioned and trying to put that also into Hydra, so you can basically debug sort of performance problems in your build. So towards the end of, in Q4, we want to actually go out and let everyone use it. You can download and try it out on your build. And at the same time, also start working on the distributed part. So when the build is too large or too big for one machine, to be able to use more machines. Maybe you have an Amazon account and you want to use AWS and so on. And obviously, if we have that, we'll also have a cloud service where you can either send your build to the Triplequote cloud or deploy it on-premise and use it there. I think that's all we have. Thank you very much. If you want to have a look at what we've done previously, there's a link to the blog. And if your company is interested in the private rollout, please come talk to us after, and we'll be very happy to talk to you and try to help. Thanks. If there are any questions, shoot them.
I'm wondering if you could show us a dashboard about that insights or metrics. How do they look like in a real project?
Sure. Well, it's not done yet. We have some sketches, but we didn't put them in the slides because it's really just raw sketches. I would not venture into it. We can talk afterwards. Maybe you have some good ideas. We're happy to hear them. So I can say that what makes it a little bit difficult is that it's not just timelines. We don't want to use something like Zipkin for showing spans. We want to add alerts as well to basically flag potential positions in your source that are issues where you want to look, and then dig into that to find more info of that particular point in code. So it's going to be a challenge to make this easy to use.
Hello. OK, so you mentioned that later on, once you reach general availability, the project will be available to open source projects.
Yes.
What would be the status of the monitoring part? Is this going to be part of Hydra, or it's a separate thing?
Yeah, it's a good question. I think our vision was to have a CI version, because it makes much more sense to have the historic view of your builds if you can tie them to a commit, because that's what sort of makes it easy to distinguish. If you build several times on your machine, it's not going to be extremely interesting. Maybe it's useful as well for the let's say individual version. I'm not yet sure. Maybe there will be part of something trimmed down, because the idea of the dashboard and UI is to actually have a web-based UI where the whole team can look at data. So I'm not sure how well that would work for an individual computer user. All right. Well, if there are no more questions, thank you all again, and grab us after the talk if you have further questions.